Hey guys, welcome to Section 1 of Fundamentals of Chemistry. We're going to be talking about metric conversions, chemical calculations, how to set up conversions in chemistry, and scientific notation. So the way that we're going to be using conversions in chemistry is that we're going to be using the dimensional analysis method. And to use dimensional analysis, you use conversion factors. Now, you already know conversion factors. If I said, just out of curiosity, how many hours in a day? You'd say, oh, well, one day is 24 hours. Unless you're a nerd like me, and then you'd say, well, actually it's 24.13, which is why we have leap years to try to gain back the day. Anyways, but in general, one day is 24 hours. So that's a conversion factor. We know that that's a fact, all right? Conversion factors, by definition, are fractions or ratios that show a relationship between two units. We use them to convert between units. So when converting between inches and feet, you know that 1 foot is 12 inches. So you could say 1 foot is 12 inches, or you could say 12 inches is 1 foot. They are both factual, and so you can flip it up and upside down as a fraction to use it either way, just depending on how it is. And I'm going to show you where you plug conversion factors into dimensional analysis in a moment. So when you're setting up a problem, the way you're going to set it up is basically in this grid-like format right here. You see that you have a value out front. This is going to be the given value in the problem. And then ultimately what you end with here is going to be what you want. Okay, so the unit that you want. We are converting units, so we really shouldn't be focusing too much on the numbers at this step. All we really want to think about is where do I need to put my units to make it work. Okay, when you put it into the problem, what you're going to do is multiply all the numbers across the top, divide all the numbers on the bottom. Okay, and you also could do, if you want to, the way I like to do it is just to literally say A times B times D in this case. So A times B times D divided by C divided by E. You hit enter and that gives you the final answer. Okay, final answer's unit should be in the same unit as D, and you'll see that in just a moment, how you set that up with the conversion factor. Some people will look at this and say, well, isn't it just a giant fraction on top of another giant fraction? Yeah, sure. So if you want, you do A times B times D, and then you write that answer down. You do C times E, you write that answer down. You take the first answer, making sure you don't lose any decimal places, divide by the second answer. It works, but it is a little bit more complicated. So I say, just get in this habit. This times that, go all the way across the top, and then divided by that, divided by that, divided by whatever. Okay, so if this had an extra step here, you would continue dividing by the denominators, continue multiplying by the numerators. So it's not until you really see how it's laid out that it starts to make sense what dimensional analysis really looks like. So what you see here is very similar to what you saw on the previous slide. It's just showing up slightly different. So I'm going to draw the lines in so you can see them, just so you're not confused. Okay, so you see that it's still a grid. And in this question, it says how many seconds are in 2.3 days. Now, you may say, well, I can do that in my head because I know that there's 60 seconds in a minute and there's 60 minutes in an hour. Oh, you mean right here? Yeah, that's what we're doing. So you already know how to do dimensional analysis. You just haven't necessarily set it up in this format. So really all you're learning is to take what you already do in your head and put it on paper. You know that if something is $1.99 a pound and you need 2 pounds of it, that it's $1.99 times 2. Yeah, duh. Right? That's exactly what you're doing with dimensional analysis. You just need to set it up in a clean format, okay? When we start getting into units this year that you're not familiar with, things like megahertz and things like nanometers and things like moles and things like that, it's going to start getting complicated. So I want you to make sure that you're following what I'm suggesting for you now so that later it doesn't come around and bite you, okay? So notice here, I was given in the problem this value of 2.3 days. Okay, of course I'm highlighting red on purple, and that really stands out. So over here, I've put that out here in front, the given value. Okay, and then what you'll notice here is that the units then kind of go from top to bottom. So days is over here in the top, and essentially that's over 1, right? 2.3 days is the value that you're starting with. So over here I put days in the bottom because if I put something in the numerator and in the denominator, then it cancels out, okay? And so we want to think about this. Really don't look at the numbers just yet. Focus on the units. And you'll notice here it says the unit you want, the unit you want. They all need to be focused on the unit first. When I do this, I actually set up the units and then I go back in and plug in the numbers because it helps you make sure that your numbers are right, okay? If I say, oh, I'm starting with days, so I need to put days in the bottom of the next conversion. Cool. Well, the next logical transition would be to step down to hours, so I put hours on top. Well, hours is not the unit I want in my final answer. It is what I need to use next, but it's not my final answer because the question said seconds. So I would then put hours in the bottom of the next conversion factor. Logical progression down would be to go to minutes. Minutes is not what I want in my final answer, so I put minutes in the bottom of the next conversion. The logical progression then would be to go to seconds. Then I can start plugging in my numbers, and I say, and please make note of this. Let me see if I can highlight it over here. It's something that stands out. Just go with it, okay? Every conversion factor must be a true statement. So what I've encircled in that red box right there on the page, it has to be true. If it said 24 hours over 2 days, it's wrong. If it said 24 hours over 2.3 days, it's wrong because that's a lie. Don't lie to me. We just met each other. I told you you need to be honest. Don't lie to me. So it needs to be a true statement. Every conversion factor has to be true. So you need to, in this case, plug in the numbers to make it true. Well, 1 day is 24 hours, 1 hour, 60 minutes, 1 minute, 60 seconds. I then multiply everything across the top, divide by everything across the bottom, and I get my answer of 198,720 seconds, okay? So again, dimensional analysis, it is a normal logical calculation. All it is the format is different. So you need to follow the format that we're introducing right now. These are some standard conversion factors, and I see that the bottom one got cut off, but it is on your paper, so just glance down there. These are some common conversion factors. You will probably use these in some of your practice problems. I don't really necessarily expect you to memorize all of these. You'll see in a couple slides that some of them, like these, you will end up memorizing, but nobody needs to know how many inches are in a meter. That's stupid. So if you're given that, I'm asking you to know what to do with it. So if I said, you have 12.7 inches. How many meters is that? Okay, well then you would say, cool. Well, I know what to do with that. I know that, hold on. I know that 12.7 inches, set up my grid. I know that inches goes in the bottom and meters goes on top. That's when I plug in this true statement. 1 meter is 39.38. Excuse my handwriting. That doesn't look like an 8. That looks like a Q. But that's when I can plug in that statement and then calculate it and be done. Okay, so dimensional analysis is really just a format for using conversion factors or true statements to get a conversion done. Here's another practice. We have 10.2 gallons of gasoline, so I start with gallons out front. I put gallons in the bottom of these two so that they can cancel. Gallons to quarts is the logical progression there because we have a conversion factor for that we know of. If you knew how many liters were in a gallon, cool, jump straight to it. If you know how many milliliters are in a gallon, cool, jump straight to it. I don't, so I'm not trying to pretend like I do. So I'm trying to take those steps to get there. Gallons to quarts, quarts to liters, liters to milliliters, okay? And then if every unit cancels out and you're left with just the one that your question asked you for, then you are on the right track, okay? Multiply your numerators, divide your denominators, check to make sure that that is what you would get. Okay, scientific notation. Why do we use scientific notation? Because at some point this year, you are going to use this number. And nobody wants to write those many zeros that many times. Okay, so you would end up writing that as 6.02 times 10 raised to the power of 23. Okay, that is a value you are going to use so much this year that you will memorize it. Don't nobody need to know how many zeros are in there. I don't expect you to write that many zeros down. That's ridiculous. I want you to use scientific notation. So the question when people ask, why do I have to use scientific notation? You don't have to, but I'm going to start making these numbers annoying until you feel like you want to. Okay, so The idea with scientific notation, if you are unfamiliar, although many of you are probably at least partially familiar, you take a number and you put it into a format that really condenses it down usually, makes it a little bit more understandable. Now, obviously, sometimes in examples like this one, you're going to get weird examples where you're like, why would I put that in scientific notation? Nobody would. Nobody's going to take 54 and put it in scientific notation. However, you can, because the rules say you can, right? But numbers that are obnoxious, like 6.02 times 10 to the 23rd, is a number that needs to be in scientific notation, okay? So you move your decimal, knowing, of course, that in the number 0, the decimal is there, okay? We would move our decimal the number of times it takes to get to be behind the first real digit. We move our decimal until the number is now between 1 and 10. It needs to be greater than 1, less than 10. So the decimal needs to go behind the first real number from the left side of the number. Okay? The number of times you move it is represented as the exponent. If you move it to the left, it's a positive exponent. If you move it to the right, it's a negative exponent. Now here's how I do it. Because I wrote down here, don't forget to write my shortcut. This is how I do it. A number like 70,789. Well, is that number greater than 1 or less than 1? It's greater than 1, okay? And numbers that are greater than 1 are positive numbers. So if the original number in its standard form is greater than 1, then it has a positive exponent once you finish, okay? If the number, like 0.0898, is less than 1, okay? And that means that anything less than 1 on the number line is a negative value. So if the value starts out as a decimal or a fractional value of 1, then your exponent is going to be a negative exponent, okay? Between this dimensional analysis and this, I think now's a good time if you want to pause, do a couple of your practice problems, see if it's making sense to you, and then come back to the video. In order to make sure that you understand scientific notation, I've asked you here to practice this, put it into your calculator, see if you get it right, okay? Be careful with these exponents. When I put 5.5 times 10 to the 5th in my calculator, it should go in as 5.5 times 10 caret 5, okay? To make that even better, put it in parentheses. Okay. If you know how to use a scientific notation function on your calculator, awesome, use that. If you don't, this is how you need to do it in your calculator. It takes longer than using the scientific notation function, but it's just as effective, okay? So if you are comfortable with this method and you're comfortable with recognizing that you probably should put it in parentheses, even this value down here, then go for it. If you know the scientific notation button on your calculator or you want to ask me to look for it on your calculator and help you, I certainly can. Let me know. Run this calculation until you get that. If you don't, write on your paper that you didn't and show me on the next class period so I can help you to get that together. The metric system. Isn't it beautiful? Kind of. All right, the metric system is based on powers of 10, so it obviously fits pretty well with scientific notation because they both are representative of powers of 10. A power of 10 just means a decimal place. So if I say 10 to the first versus 10 to the second, the difference is 1 decimal place between them. Okay, for this page, if you are in honors, you should pause. And you should make flashcards for all the ones in yellow, okay? You are being asked to memorize those at this point. That is an expectation for AP and IB, so it is an expectation for honors. What you do with these is basically, when it says, let's say kilo, okay, for instance, if I'm looking here, 1,000 base equals 1 kilo. What that means is the base unit is things like meters, liters, grams. Okay, so if I'm looking at a kilogram has 1,000 grams. Okay, a kilometer has 1,000 meters. A kiloliter has 1,000 liters. A nanogram has a gram is made up of 1 billion nanograms. Okay, so it gets a little tricky, and sometimes using the order of magnitude can be helpful. But on the next slide, you're going to see how you can put this into a dimensional analysis problem. To get through a conversion factor, you always need to go through your base unit. Now, if you know in your head and you don't make a mistake how to jump between them, hey, go for it. But if you're making mistakes, go back to this, okay? So you should always try to go through your base unit. In this case, you were asked to convert 430 centimeters to meters, so that means that I need to get 2 meters, obviously, because that's my base unit, okay? My first step would be to put what I start with out front, okay, that's my given, set up my dimensional analysis. That unit goes on the bottom so that ultimately they can cancel, and the unit on top will be left over, and that's the one I want in my answer, okay? So remember, every conversion factor needs to be a true statement. And if you go to the previous slide, 100 centimeters is equal to 1 base. So that's true. 1 base unit, or 1 meter, is equal to 100 centimeters. So I would take 430 times 1 divided by 100. That gives me 4.3 meters. Down here, you'll see a better example because you actually go through the base unit to get there. 15 kilograms to milligrams. So kilograms, 15 kilograms goes out front. I know that that unit is not what I want my answer in, so I will have to cancel it out at some point. And I'm going to go through my base unit first. So kilo is 1,000 bases. So if it's a kilogram, that's 1,000 grams. So that's what I've set up here as a true conversion factor. I've also looked and I saw that 1 base is 1,000 millis. So 1 gram would be 1,000 milligrams. 1 meter would be 1,000 millimeters, etc. Okay. So once I set that up, I take this, my original value I started out front with, multiply it by the next number up top, multiply by the next number up top, divide by the numbers on the bottom, and I get 15 million milligrams. Okay. Finish your practice problems on this packet and come in next class with questions. Coming in and saying, I don't get it, is not a question. So formulate a question, and if you're struggling with something, plan to do some access time because we want to make sure that we don't slow down too much, okay? All right, so I will see you next class, and hopefully your practice goes wonderful.